So welcome to Math 389, Operations of Order. And so what I want to do today is I want to talk about generating functions. And so I don't think we've done too much on generating functions in this class. Did we do Benet's formula in this class already for Fibonacci's? Okay, I didn't think we had done that. And so we're going to do Benet quickly, and then we're going to move to a more interesting situation. And part of this is, as you get older, okay, so at least two of you, maybe three of you have reacted positively. So does this mean you've actually read the article, or do you just know the article?
No.
Okay, you should read the article. So I was a grad student at Princeton, and they actually had Wigner's Nobel Prize displayed in front of the math physics library. Right. So you could give, I think, an entire course on some of his observations. It's why do we keep seeing the same mathematics in so many different places? And why does mathematics seem to do such a great job describing the real world? Two very related questions. Way above my pay grade as a professional mathematician. But I can do the mathematics and then be happy that if I replace the label mass with charge, the same behavior seems to flow. So as you get older, one of the things they recommend is, read the papers of the masters. So take a look, you'll see what Wigner was saying about mathematics occurring in so many different places. So Fibonacci numbers. All right, so everybody hopefully has seen, the Fibonacci numbers a couple of times. There's lots of different ways of defining them. I will define them as F0 is 0, F1 is 1, and then in general, Fn plus 1 is Fn plus Fn minus 1. So this is a recurrence relation of depth 2 constant coefficients. There's lots of ways of generalizing this. If I told you, and I know somebody here owes me a paper on this, that your grade depends on calculating the 100th Fibonacci number by hand, would you take it? Sure. You can do the addition slow enough that you'll be fine. What if I ask you to do the millionth or the billionth? At what point do you say, no, thank you?
After a couple of thousand.
After a couple of thousand. And so, how quickly do the Fibonacci numbers grow? And is there a closed form expression for them? Right now, the Fibonacci numbers are trivial. There's no mystery. I can just calculate by brute force any Fibonacci number. But by using the recurrence relation, I have to go through the previous ones. Is there a way to jump to a specific Fibonacci number? My mother recently sent me a picture of a standard math shirt. My password is the last n digits of pi. There is a formula that allows you to jump to a specific digit of pi without calculating previous digits. It's working, I think, base 16. It's a wonderful formula. So how can we calculate the Fibonacci numbers? One thing is we can try to estimate their growth rate. So this is one of the general themes is upper lower bounds. So for an upper bound, we know Fn plus 1 equals Fn plus Fn minus 1. That's going to be less than or equal to Fn plus Fn, which is twice Fn. So this tells us that the Fibonacci numbers are growing slower than 2 to the n. So this implies, Fn is going to be less than or equal to 2 to the n. What about a lower bound? Well, if we want to do a lower bound, Fn plus 1 equals Fn plus Fn minus 1 is going to be greater than or equal to Fn minus 1 plus Fn minus 1, which is 2 Fn minus 1. And so that basically implies Fn is, in quotes, it's 2 iterations. So each iteration is really like a square root of 2. Right? Because if I do 2 iterations, root 2 times root 2 is now 2. Because I went from Fn plus 1 to Fn minus 1. The index went down by 2. That was a factor of 2. So when it goes down by 1, it's kind of like a square root of 2. And the reason I have to put things in quotes is because, unfortunately, I start 0, 1, 1. So F2 is not root 2 times F1. But eventually this kicks in. So basically, we get root 2 to the n is less than equal to fn is less than equal to 2 to the n. Maybe fn is growing like some constant to the nth power. And that's a reasonable thing to conjecture based on this. And the standard way to prove this is to say, so let's try, fn equals r to the n. Then you would get r to the n plus 1 is r to the n plus r to the n minus 1. So you get r to the n minus 1, r squared minus r minus 1 equals 0. So r equals 0, or r squared minus r minus 1 equals 0. The roots of this is the quadratic formula, is 1 plus minus root 5 over 2. And so we now see that if fn is r to the n, then either it's 0, well, that's kind of a boring solution to the recurrence, or it's 1 plus root 5 over 2 to the n, or 1 minus root 5 over 2 to the n. And then you notice that the recurrence relation is linear. So the general solution is going to be some constant times 1 plus root 5 over 2 to the n, and then another constant, 1 minus root 5 over 2 to the n. As f0 equals 0, f1 equals 1, this is going to imply alpha is 1 over root 5, and beta is negative 1 over root 5 with the normalization we have. This is just straightforward algebra, right? And so everybody here has at least done linear algebra. So all I have to do is I now have 2 equations and 2 unknowns for the alpha and beta. If I take n equals 0, I get alpha plus beta equals 0. So alpha is minus beta. If I take alpha equals 1, I get alpha 1 plus root 5 over 2. Now, what's nice about this is less than 1 in absolute value. So fn is approximately 1 over root 5, the golden mean. We'll call this the golden mean, to the nth power. So because it's less than 1 in absolute value, when n is huge, it's a negligible difference. So we now have a formula. This is called Binet's formula. The key step was this divine inspiration. So this is an upper level class. In this class, we actually cover very little material. We spend a lot of time talking about how to think about things. What is the biggest problem about divine inspiration? You have to be divinely inspired, right? Once I'm divinely inspired, it's easy. We do not attack people who try to solve this other ways, but we needed to know that we should try r to the n. Now, sometimes you start having various techniques and you've seen a lot of similar problems, so you have natural things to try. There is another way to attack problems like this that are more mechanical. Because this is an upper level class, I'm not going to write this down. I'm going to just give this to you and you're going to have to solve it in your heads. I want you to find the roots of x squared minus 7x plus 12. 3 and 4, and you did that in your head almost before I finished saying it. Thank you for waiting so that it's clear that you're not a plant. So how did you do it so quickly? X squared minus 7x plus 12. How did you do it so quickly? So how did you know to do it as x minus 3, x minus 4? The roots?
Well, the constant term is the product.
The constant is the product. So I have a plus 12. And because the x term is negative, I know I need 2 negatives, because that's the only way the product can be positive. So if I want things to multiply to 12, I've got 12 and 1, 6 and 2, 3 and 4. And I want things to add to negative 7. So you can just do this in your head. If you weren't able to see that it factors as x minus 3, x minus 4, you obviously should not be in this class. But what would you do if you didn't see that? So what would you use to do it by brute force? Okay, but what if I give you something that doesn't have nice roots like that? Quadratic formula. So, worst case, you would use the quadratic formula, right? And so we have a way that will solve it. It may not be a way that we enjoy, but it's not terrible. Okay, so we were just talking about the Fibonacci numbers, and now we're about to go into Benet's formula. Okay, and so I'll just go here. So I'm not going to go through all the algebra. I'll just quickly throw it on the board. The way it works is you create what's called a generating function. And so g of x is defined as the sum and goes from either 0 to infinity or 1 to infinity of fn x to the n. The first time you see this, this should look absurd. I want to understand the Fibonacci numbers, so I create a function that's basically like a Taylor series with the coefficients of the Fibonacci numbers, which is what I'm trying to find. How is this going to help me? Well, the thing is, you actually know all the Fibonacci numbers. You just need to extract the knowledge. Because once I give you the initial conditions and the occurrence relation, there's no mystery in the Fibonacci numbers anymore. We need to somehow get a closed form expression for this generating function g of x. And if we get a closed form expression for g of x, we can then hopefully pass that to information about the fn's. And so what we do is, let's look at, and again, this is playing index of summation games. How many of you have taken a differential equations class? Okay, so you should have seen series expansion methods. This is very similar to the series expansion methods. So if we look at, fn plus 1 x to the n plus 1, well, we can then use the recurrence relation to write that as fn plus fn minus 1. And then when you look at this, you see, wait a minute, that's an fn, and this is an x to the n plus 1. The generating function has the subscript and the power the same. Why don't I just take this 1 and pull it outside and just factor out the x? And that's what we get over here. And then similarly for the other one, we have an fn minus 1 and xn plus 1. The first thing I do is I shift the index of summation, and then I pull out 2 powers of x. So very straightforward stuff, and that gets us to this equation here, where on the left I'm summing from 3, and then I have a sum from 2 or a sum from 1. One of them has an x, one of them has an x squared. All of these are close to the generating function g, but not quite. They differ by a small amount. Well, now what I do is I take the sum that goes from 3, and I extend the sum down to 1. Well, I can't just put in extra terms, but I can if I then subtract them. And so now everything is fine on the left-hand side. And then similarly for the next one, I want the sum to start at 1, so I have to subtract the 1 term there, and I don't have to do anything for the last one. And the reason I'm not starting my sum at 0 is because f0 is 0, there's no reason to hold it. And so I now get g of x. I know f1 is 1. I know f2 is also 1 with my notation. And so when the dust settles, I have g of x on both sides of the equation. And what's nice is the coefficients of g of x on both sides are not the same. It's 1 on the left-hand side, it's x plus x squared on the right-hand side. So I bring that over, I solve for g of x, and I get g of x is x over 1 minus x squared. This is beautiful. We have a closed form expression for the generating function. And now we want to use that to get information about the Fibonacci numbers. Does 1 over 1 minus x squared, there's a factor of x, but the x in the numerator is easy. It just shifts everything by 1. So I can write this as x times 1 over 1 minus x squared. Does that look like anything you've seen before? Where have we seen something like that? Geometric. So this looks like 1 over 1 minus r with r equal x plus x squared, or x times 1 plus x. So that means, the sum, n greater than 0 of fn x to the n is just going to be x times 1 plus r squared plus r cubed plus ... or x 1 plus, now I'm going to have, the first term is going to be x 1 plus x. The next term is going to be x squared 1 plus x squared plus x cubed 1 plus x cubed plus ... And now the only way these infinite polynomials can be the same is if the x terms match, the x squared terms match, the x cubed terms match. Why am I not happy? Why can't I just match things up now?
The extra parts of X.
So let's multiply things out. So the first, when I multiply it, I'm going to get x. Then I'm going to get x squared 1 plus x. Then I'm going to get x cubed 1 plus x squared. Then x to the 4th 1 plus x cubed plus dot dot dot. This is the only x term. But over here, this has x squared and x cubed terms. What about this one? X3, X4, X5. What about the next one? X4 all the way up to X7. So the problem is, if I try to attack the problem this way, it works, and I'm only going to have finitely many terms that arise and are going to come into getting, say, F4, F5, F6, F7. Eventually, if I only care about F2, I only have to look up to here to figure out what F2 is, because there's no x squared terms beyond this point. If I want to calculate F3, I only have to look up to here. If I want to calculate F4, I only have to look up over here. But unfortunately, if I want to calculate F4, I've got terms from here and here. And so it gets worse and worse the further down you go. So I give you credit for recognizing that this was the geometric series, but it's not going to lead to a pleasant formula. So you were being inspired by a false god. So what is a better way of doing this other than saying it's not 1 over 1 minus r? Differentiating identities is not a bad idea. There's something better. Differentiating identities is going to get very bad because you're going to have the x and the x squared, and that's going to give you bad powers. But I do like the idea of just charging in and replacing the derivative of a sum with the sum of the derivatives. Partial fractions. So if you have a list of which technique from calculus do you hate the most, the answer is either partial fractions, or if it's something else, if you remind the person, what about partial fractions? Oh yes, I forgot about that. I was so traumatized by it. I just blanked it. Yes, you're right. I hated that. Right? There is a reason why we learn partial fractions. Partial fractions is useful. So we factor 1 minus x squared. We can write that as 1 minus alpha x, 1 minus beta x. And then you can write this as 1 over 1 minus x squared as a over 1 minus alpha x plus b over 1 minus beta x. So this is just standard partial fractions. Now we can use the geometric series, and because of this, when we expand now, it's going to be pure, and you're not going to have different terms having the same power of x. And when you do the algebra, this is what you get for the values of alpha, beta, capital A, capital B. And this leads to Benet's formula, to me, one of the most beautiful formulas in all of mathematics. And the comment I always love to say is, imagine that you were beaten up on the streets by a number, and there's a police lineup, and you have to identify which number did this to you. And you didn't get a really good look at the assailant because it was, Pi Day and you were celebrating, but you did notice that it was an integer. Does this look like an integer? So as a fun exercise, what can you replace the 5s and the 2s by and have this still be an integer for all values of n? This is always an integer. It's a lovely formula. All right. So this allows us to jump to any Fibonacci number quickly. And because the second factor is less than 1 in absolute value, for very large n, like 3, 4, your Fibonacci number is whatever integer is closest to the first. So that's really nice. So you can calculate these very quickly. So I started the day with Wigner's paper and this idea that mathematics not only describes the world, but the same mathematics describes different parts of the world, which is just a shocking thing, that we don't have to keep developing new mathematics to describe new situations. It's the same ideas again and again and again. So how many of you have seen the Catalan numbers? All right, where have you seen the Catalan numbers? And in what way? What were we doing Catalan numbers for?
Oh, we're counting the sums with the grid.
Okay, so you talk about walking. So one way to see the Catalan numbers is, I'm going to give you a grid, and I do apologize that you're going to hear some of the same lecture again, but there'll be something new later. So 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And so here's the point 0, 0. Here's the point n, n. And for some reason, I never want to be above the main diagonal. So I want to look at how many paths can I take and stay below the main diagonal. So stay below the main diagonal. So one possibility is I could do a path like this. Oops. Oh, I erased all the way like that. Wow. So that would be one path. Another path is maybe I could go like this. Maybe another path. Lots of different paths. And so the question becomes, how many different paths can I have? There's another definition. I know there's lots of definitions. Does anybody know another definition of Catalan? So it's legal listing of n left and right parentheses. So you never see more right than left as you go down. So for instance, just making up numbers, 3 plus 7 divided by 4 times 8 minus 16 plus 11. And then I guess I don't technically need one, but I'll put it in. That would be legal. And as I'm walking through here, I'm plus 1, plus 2, plus 3, and at this point, plus 2, plus 1, plus 2, plus 3, plus 4. Oops, wait, did I make a mistake?
3 plus 2.
I'm sorry?
3 plus 2.
Oh, that should be plus 2. There you go. I added good. Plus 2, plus 1, plus 0. And so I ended up, with no extra parentheses. These two problems are the same. Because if you think about this, we're moving either north, which would be the left parentheses, or we're moving east, which would be the right parentheses. And if we have to stay below the main diagonal, it's really equivalent to.
Is it east for the little parentheses? Since you want to have more east than north.
Oh, sorry, you're right. Thank you. So we'll make east be the right parentheses and north be the left parentheses. Yes. And so we never travel above the main diagonal. So we'll let Cn be the nth Catalan number. Can you give me, and they can be stupid upper or lower bounds. So have you been accepted yet, or are you still?
I'm committed, yeah.
Okay, so you're committed. So even if you screw up today as a visitor, nothing's going to happen to you.
Well.
So, all right. Well, I do have some pull with admissions. So if you get this wrong, I will call and I will say that they should withdraw your admissions. Can you give me a lower bound for Cn? that you are willing to, your academic future now depends on this, that you are guaranteed will work?
1.
1. You sure is that what you want to do? Is anything better than 1?
0.
So
Yeah.
0 is really safe. Or -1. 1 is probably safe, right? These are the safe. Can you give me an upper bound that you'd be comfortable with?
Infinite.
Infinite,
Yeah.
right? If your life is on the line, be safe. Can you give me a finite upper bound? Can anybody give me a finite upper bound that they are confident about?
N factorial.
I'm sorry?
N factorial.
Why n factorial?
It's like all the ways you can. That seems big enough.
Well, how many steps do you have?
Yeah, 2 minutes.
We have 2n steps.
I'll put 2 N factorial.
But is it 2n factorial?
Seems big enough. 2 to the 2.
So for each move, you can either go north or east,
Yeah.
right? How many moves are you doing? So, I'm sorry?
If you move all the way to the right and then up.
So I think 2 to the 2n would be a safe upper bound. At each step, I either move east or north. This would allow me to have all east, which would be absurd. This would have all north, that's fine. It's an upper bound. So if you look at this, this is much better than these factorial bounds, which again, the factorial bounds might have been fine, but that would require me to do a little bit of thinking to see if your n factorial was okay. 2 to the 2n I can be very confident about without doing much work. Unfortunately, 1 and 2 to the 2n differ by a lot. They're not even close, right? One of the things we've done in the past is we've looked at 1 plus 2 plus 3 plus ... plus n, and we know this is n plus 1 over 2. Seen this? And so one trivial upper bound is we know if we call this sum Sn, it's clearly less than n times n, which is n squared, and it's clearly greater than n. Just take the largest term, but those bounds differ by a lot. So we don't know the true order of magnitude. But what we could do is we could look at the last half. We could look at 1 plus 2 plus, let's say, n halves plus n halves plus 1 plus ... And I'm not going to worry about, is n even or not, because this is just informal. And now if I look at these are all at least n over 2, and we have n over 2 of them. So now we still know it's less than n squared. That hasn't changed, but now we know it's at least n halves times n halves, which is 1/4 n squared. And so even though we don't have the correct value, we at least have the correct independence. We know that it's on the order of n squared. I'm really disappointed at you guys. We got a guest here, and our bounds are off by this much. We've got a 1 and 2 to the 2n. So can you either raise the lower bound or kill the upper bound, or both? Any thoughts?
Super small saving would be to say 2 to the power of 2n minus 1, because like at most half of the paths will stay under the line by symmetry.
So it's if we were talking about the US debt, if you could decrease the debt by a factor of 2, wonderful. Sadly, this is not the debt, but it's something. So yes, that would be a percentage savings by saying half the path should, well, you gotta be careful because some paths could be both above and below. But
what I'm saying, like
yes,
at most it's
at most it's 1/2 total paths. Yes, because by symmetry you can reflect, and whatever path is all below is also, there's a corresponding one that's all above. So it's at most 1/2 2 to the 2n.
Well, how about like 2 intrusive?
Ah. So now that's a much better bound. So claim Cn is less than or equal to 2n choose n. And the proof is we have 2n moves, n are north, and n are east. So clearly, it's at most 2n choose n. Unfortunately, some of these might go above. Might go above, so upper bound. Okay, now, have we made progress? How big is 2n choose n? This is 2n factorial over n factorial, n factorial. If you know Stirling's formula, you can try to use that. Can anybody give me an upper bound for 2n choose n? To the n. So we know 1 plus 1 to the n is the sum, I'm sorry, to the 2n. K goes 0 to 2n of 2n choose k, 1 to the k, 1 to the 2n minus k. Right? And 1 plus 1 to the 2n is just 2 to the 2n. So as the binomial coefficients are non-negative, we know that this is clearly less equal to 2 to the 2n. Okay. But what's the lower bound on 2n choose n? Well, I want a lower bound on 2n choose n. So what can you tell me about binomial coefficients as I move from the edges? It gets larger. So this is going to be less than equal to 2n choose n. And how many binomial coefficients do we have? Almost.
Plus 1.
2n plus 1. So this is the largest coefficient is the middle. So you have to prove that, but if you're willing to use that, then we get as a lower bound 2 to the 2n, 1 over 2n plus 1. Now, if n is large, that's a savings, but it's not a huge savings. It's better than the 50%. Your percentage-wise, it means that it becomes 0% of 2 to the 2n. But on a log scale, it means effectively you've done nothing. So unfortunately, it's an improvement, it's progress, but there's still a huge difference between the up and the lower bounds. And so the question is, can we get the upper bound down a lot more, or can we get the lower bound up? Do you know a large number of paths that will have to work that you could count? And so what we can do now is we can try to come up with a recurrence relation to solve this, and then try to use the idea we just saw with Benet's formula, either divine inspiration and write down what the Catalan numbers are, or create a generating function and have that just spit out the answer. And so I'm going to try to do it slightly differently than we did before, so you're seeing something a little bit new. Now, one of the things Williams does extremely well is they let us know when prospective students are coming. They give us plenty of notice. They warned us, I think, either at the start of the semester or before the semester, this day is when prospectives can come so that we can adjust things. And so I adjusted things for my probability class. What are we supposed to be doing today? We're supposed to be doing random matrix theory, right? We're not doing random matrix theory right now, right? We are. Why are we doing random matrix theory? These are the moments of the cell of the semicircle distribution. They're the Catalan numbers, and it comes down to combinatorial matchings. So what we're doing today, right now, is actually related to the semicircle, and that's why we actually skipped chapter 16 and went to chapter 17 in the book, and are going to come back to this because this was much easier for someone to just walk into and make sense of today's lecture. So let's now come up with a recurrence relation. So Catalan recurrence. so much of math is trying to figure out what is the right thing to study. And so what we're trying to do is we have our grid and we have to stay below. And so we have like some kind of path like this. And I want to figure out how many paths are there that stay below the main diagonal. And we want a way to classify them. And so a really good way to do this is, Cn is the number of paths on or below the main diagonal from 0, 0 to nn. Bn, let's not do Bn, let's do Bk, is the number of paths on or below main diagonal from 0, 0 to kk and first hit the main diagonal at kk. Another way of saying this is below, right? So I can either have the word on or below, and then just say by on or below, I mean below. And the reason is, if I'm walking from 0, 0 to nn, I can split all the paths as to when is the first time they hit the main diagonal. Does every path have to hit the main diagonal at least once? Why? It has to hit at nn. So if I give you a path, for one path, I can look to see where does it hit, and then it can continue. And then for another path, I can see where does it hit, and then it can continue. And so for each path, it has a place of first hit. And then once you hit, how do you figure out how many paths you have from there onward? So you could do that, and then you could have a sequence of hits, right? So you could look, where do you hit the first time, where do you hit the second time, where do you hit the third time? And if you don't hit at nn, you have to hit again. But let's say we hit here at kk. So how many paths are there from 0, 0 to kk, and you first hit main diagonal at kk? How many such paths are there? So how many paths are there from 0, 0 to kk, and the first time you hit the main diagonal is at kk?
CK times C.
Nope.
Oh, wait.
It's a definition. It's on the slide. So I want to know how many paths are there from 0 to 0 to kk, and the first time I hit the main diagonal is at kk. What are we calling that? That's just bk. Right? That's just bk. Now we want to go from kk to nn, and I don't care if I hit or not. How many paths are there from kk to nn? Cn minus k. So this is the same as number of paths from 0, 0 to n minus k. So this is going to just be C n minus k. Right? So we just multiply them. So now if I want to find a formula for Cn, where could the first hit be? I'm sorry? K equals 1. So then that would be B1, and then what would be next? So there's always the danger that my index might be off by 1. And if so, I apologize. And then what would the next one be? So it could be B2 and then Cn minus 2 all the way down to my first hit could be at n, and then it would be C0. Okay. So do we all agree that this is a recurrence relation? This is not as warm and friendly of a recurrence relation as the Fibonacci's. It has products of terms, and the number of terms grows within. And it involves two different recurrence relations. Fortunately, there's a really nice relation between the B's and the C's. So if you think about what's going on, so let's say, as always, here's my diagonal. Here's KK. Here's 0, 0. Now I want the first time I hit to be at KK. We know we have to start, whoops. We know we have to start off by going one step east. What's our final step? Going north. So we know we have to end like that. So we have K minus 1 east left over and K minus 1 north left over. And we can't hit the main diagonal, right? So we can't get above that line. So what's the relationship? BK is equal to what? Almost CK minus 1. So even though I introduced B, it turns out B is trivially related to C. This is nice. And now what does this mean? Well, we can come back over here. We have our formula. So I will copy the formula, come over here, and here's our formula. And now, I don't know, can I do this? Yes. I can now just, I won't, I'll just write it. So the new formula we get would be Cn, so B1 is going to be C0, Cn minus 1, plus B1, Cn minus 2, plus dot, 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 plus, sorry, that should be a C, C1. C1, Cn minus 2, and then we would have over here Cn minus 1, C0. So Cn is going to be the sum of Ck, Cn minus 1 minus K. K goes from 0 to n minus 1. So that's our recurrence relation to solve. If you've seen a lot of things with convolutions, I know some of you have, this is a convolution. There's actually hope for studying something like this. So, again, I care and I don't care about the answer. I care more about how can you attack something like this? Can you somehow use this to get a sense of how large Cn could be? We have bounds on how large Cn could be. Can we feed that into here? We could get a small reduction, but nothing significant, unfortunately. If we knew the C's were much smaller than the 2 to the 2n, that would be a little bit better. So the question is, how would we solve something like this? One of the things that's a little bit annoying is this, minus 1 and plus 1. So instead of studying this, you might study instead Cn plus 1 is the sum k goes from 0 to n of ck Cn minus k. Just, which way is going to be the best way to do the algebra. So we want to find a generating function. Any thoughts what the generating function should be? How should we define the generating function?
C0 plus C1.
Yeah, I mean, we have nothing to do but the sum, C I'll do Cm x to the m. M goes from 0 to infinity. I didn't mention this before, but you always want to make sure do things converge. You know, as you know, Cm is an absolute value less than or equal to 2 to the 2m. That implies it converges if the absolute value of x is less than 1/4. Because then it'll be bounded by a geometric series. This is why some of the estimates we did before for the Fibonacci numbers were useful, that the generating series will converge as long as x is sufficiently small. We know the Fibonacci numbers are going no faster than 2 to the n, so if x is less than 1/2, the generating function will converge. We know the Catalan numbers are not going faster than 4 to the m. The series will converge if x is less than 1/4. All right. I mentioned convolutions. Has anybody seen convolutions before? What should I do to the function g of x? Square it, right? If I look at g of x squared, that's going to be the sum. Let's do, Cm x to the m, and then that's the sum over m. And then we'll have a sum, let's say, we'll do L. L goes from 0 to m, infinity, Cl x to the m. That's going to, x to the L, thank you. Then that's going to be the sum of, let's say, an x to the n. And we need to figure out what those coefficients are. And if you think about what's going on, we have C0 plus C1x plus C2x squared plus ... C0 plus C1x plus C2x squared plus ... And when we multiply, we're going to get C0 squared, right? And then the next thing is going to be the x term, C0 C1 plus C1 C0 x, plus the next one is going to be C0 C2 plus C1 C1 plus C2 C0 x squared plus ... What do those look like? So what does this equal? So this is C2. What does this equal? What does this equal?
C0. That's 1. Do it if C0 is 1.
So if I take over here, if I take n equals 1, then I would have 2 terms. So if I take n equals 0, I would have just 1 term. I would have C0 squared. So this, I think, is just C1. Does that look right? So it looks like g of x squared is equal to C1 plus C2x plus C3x squared plus ... How close is that to g of x? So if I were to multiply, let's see. I could multiply this by x and divide by x. And then I would have C1x, that would all look good. But what would I be missing? All right, so how do I get that first term that I'm missing? Plus C0 minus C0, right? And so now this is going to be, I think, g of x times x minus C0 over x. Oh, sorry, no times x, g of x. Yes, so it's g of x up to, oops. Up to here, it's g of x. So it's g of x minus c0 over x is g of x squared. All right, so now we have g of x squared is g of x minus c0 over x. And what is c0? C0 is 1. So we get x g of x squared equals g of x minus rho minus 1, or x g of x squared minus g of x plus 1 equals 0. What do you think? How?
Well, treat x as a constant.
Okay, and do what? How do I solve this? Yeah, use the quadratic formula, right? So use quadratic formula. Variable is g of x. And the coefficients are x, -1, and 1. Therefore, g of x is equal to -b plus or minus the square root of b squared minus 4ac, right? All over 2a. When I look at this, I actually see something that's reasonable. The 4x looks reasonable. What can you tell me? Again, it just wasn't your day after being beaten up by a Fibonacci number. Later in the day, a Catalan number kicked you as well. What kind of numbers are the Catalan numbers? Integers. What should be true about x where we're using this?
It's less than 1.
Less than
1.
1/4. If x is greater than 1/4, you're going to get an imaginary number. Remember how earlier we said that the series will converge if x is less than 1/4. If we put that in right here, that's looking reasonable. And maybe this is telling us that the Catalan numbers are actually close to 2 to the 2n. But beyond that, things are breaking down. But this is looking pretty reasonable. Unfortunately, there are 2 roots now. Do we think both roots work?
Well, we can always try that, so you can numerically calculate the c inside.
So there shouldn't be 2 different generating functions, right? Are there any values of x where we know the answer for the generating function? 0. Now, what is g of 0? That's just c of 0, which is 1. So we can look at the limit as x goes to 0 of 1 plus the square root of 1 minus 4x over 2x, and the limit as x goes to 0 of 1 minus the square root of 1 minus 4x over x. Which of these is going to have a nice limit as x goes to 0? The first one with the plus sign or the second one with the minus? Second one. That goes to infinity. It can't be that. So this is the answer. So g of x is 1 minus the square root of 1 minus 4x over x. Okay. So now we need to extract information. So g of x is, the sum, cn x to the n is 1 over x, 1 minus 4x to the 1/2. Does anybody remember we need to expand 1 minus 4x to the 1/2? So we need Newton. So if I give you something nice like 1 minus 4x to the 3rd power or the 5th power or the 1701st power, that's the binomial theorem. We need the binomial theorem in a more general setting. So how do we do this? Do you remember?
Yeah, it's basically just by nomial. Right? Instead, you have n replaced by 1/2.
So let's say we have f of x is 1 minus, instead of x, I'll use u. Let's say we have fu is 1 minus u to the 1/2. What's f of 0? 1. F prime of u is going to be 1/2, 1 minus u to the minus 1/2 times -1. And so f prime of 0 is equal to -1/2. Now, f double prime of u is going to be 1/2, -1/2, 1 minus u to the -3/2. We have another -1. Oh, so the two negative signs are going to reinforce and it's going to stay negative. So what would f double prime of 0 be? Minus 1/4. Oh, plus 1/4. Okay. Wait a minute. Oh, I'm sorry. There was an extra minus sign that I forgot. It should be minus 1/4 because when we took the derivative before, we had this -1 over here. So it should be -1 squared. Right? Because if you think about it, we're always going to get a minus sign from the exponent now, and we're going to get a minus sign from the 1 minus u. What's the third derivative going to be? It's going to be 1/2, and then I can do it as 1/2 and then 3/2. 1 minus u to the -5/2. And I know the signs are always going to be minus from this point onward, so I'll just put a -1 over here. So f triple prime of 0, how do you want to write that? It's not immediately clear. Let's do another one. The fourth derivative is 1/2, 1/2, 3/2, 5/2, 1 minus u to the -7/2, -1. Now, when you do your Taylor series expansion, the Taylor series expansion of a function is the sum of the nth derivative at 0, x to the n, divided by n factorial. Right? Look at how nice the bottom is. The first derivative has 1/2, the second derivative has a 1/2 squared, the third has a 1/2 cubed. So we're going to have, in the nth derivative, we're going to have n powers of 2. The numerator is 3 times, it's 1, then 3 times 1, then 5 times 3 times 1. These are the double factorials. These are the every other. So the nth derivative at 0 over n factorial, I'm going to have a negative sign. I'm going to have 2 times 4 times 6 ... times 2n. The numerator, I'm going to have a 2n minus 1 ... times 3 times 1.
Express the double factorials as a fraction of usual factorials, right?
So how do we want to write this?
Or we can do it 1/2.
So this is now playing games of algebra. What's the best way to write this algebra? The first thing is to make sure we haven't made a mistake yet. And then have we gone a little bit too high? So is it really 2n minus 1, or is it something slightly smaller? So here, when we're doing the third derivative, we go up to 3. The fourth derivative, we go up to 5. The fifth derivative, we would go up to 7. So maybe 2n minus 1 is not the right thing. So the fifth derivative, we're going up to 7, not 9. So I think this is 2n minus 3 here, not 2n minus 1. So it's very easy to make a small. So I think it goes up to 2n minus 3. All right, now that works. If I take n equals 4, that's going to go up to 5. That matches now. Okay. So now I want to somehow get a binomial coefficient from this. And this is the correct way to do the expansions, right? Yes. So we had the n factorial. We have all the powers of 2, so it's like this. Does this look like a binomial coefficient? What do you think Cn should be? So, I'm sorry? Well, we had upper bounds and lower bounds, right? What do you think? You know, we know Cn was at least 1. That was our crappy. And what was our upper bound? We actually beat that a little bit. We got 2n choose n. So that gives us some thought as to what this might be.
Wait, but then if we plug in 4x, when we differentiate it, we should have the extra power of 4.
Yes. So we'll be getting large powers of 4s that will be coming into play, right? And that will be enough to make these numbers larger than 1, which is good. We're going to have to shift things a little bit. Notice one term is positive and everything else is negative. Well, if you look at what happens is we have 1 minus. So the 1 minus, that's going to kill the 1. And then the negative is going to make all the negatives positive, which is good, because the counts should be positive numbers. Great. The 1 over x is going to shift things by 1 in terms of which index we're looking at. Okay. So this is beginning to look like it might be something like 2n choose n. We can see a lot of the ingredients. The minus signs are all going to go away. The powers of 4 are going to greatly help us. But it's what's the best way to see the algebra? And it may be better not to write it like this, but to write this as negative 1 times 3 ... times 2n minus 3, and then leave it as 2 to the n, and then n factorial. Because we're trying to get something that looks like maybe 2n choose n. Notice we have something that's looking a lot like all the odds. And so we've got just a few minutes left. And so this is where the problem is getting harder. So some kind of divine inspiration. We've got something like this, right? And we want something like, 2n choose n with maybe 1 over n plus 1 or something like that. Well, I clearly want another n factorial down below. So let me put an n factorial down below and an n factorial up above. Well, notice I kind of have almost all the odds, but I'm missing 2n minus 1. So maybe I do something like that, and now I have all the odds going up to 2n minus 1. And then if I put in an extra factor of 2 to the n, then the 2 to the n times n factorial is going to give me all the evens. So maybe if I do this, I now get upstairs 1 times 2 times 3 times 4 times 2n minus 3 times And I gotta be, do I have 2n minus 2? I have 2n minus 2. I have 2n minus 1. And do I have 2n? And then down below, I have, I think 2 to the n, 2 to the n factorial, and a 2n minus 1. So I might be, okay, so this is not looking so bad. So this is looking like negative 2n choose n with a 1 over 2n minus 1. So I might have made, and again, we have to shift the indices a little bit. I would not be surprised if I made a small mistake. But this is enough in principle to show you that we actually do see the binomial coefficients emerge. Okay. And so we're going to shift things a little bit. I think it's 2n choose n with a 1 over n plus 1 outside. So this is a little bit off, but it's close. So, fix it. So we have 2 to 3 minutes left. And now my question is generalizations. So what is your first generalization of Catalan numbers? So what would be your first generalization of Catalan numbers? So we did this. Higher dimensions. Good. So, and I'm not even going to try to draw this well, but, now say, something like that. So higher dimension Catalan numbers have been discovered and studied. What's another generalization? So initially we had to stay below the line y equals x. Yeah, so what if I give you different lines? Now, do you want to do lines? Yes, to do some kind of function. So I give you some function, f of x. So f of x is, let's say, increasing. F of 0 equals 0, f of 1 equals 1, and then you can just rescale it. And so we'll call these f Catalan. I don't know if anybody has studied f Catalan. What's the most natural f Catalan number to look at? Well, if you take f of x equals x, that's the Catalan numbers. So, yeah, x to the m. So you could look at x to the m Catalan. Try m equals 2. So I have no idea if anybody has ever looked at, I want to go from 0, 0 to n, and I want to stay below the line y equals x squared. You could, of course, even go the other way, and you could allow yourself maybe to have something that goes above the main diagonal, but you can't get too far above. I'll let you go over a little bit, but I won't let you go over by massive amounts. And so again, I have no idea if anybody has looked at these. If you're interested, do some quick Google searching. With like 2 seconds, I was able to find higher dimensional Catalans. And I didn't come up with this idea of Catalan until I was walking down the stairs. So I haven't had a chance to search for it yet. But this is how math research starts. Take something you've seen and see how can you push it. So anyways, we will see the Catalan numbers when we continue on Tuesday, because these are going to come in as the moments of the semicircle. But I thought it was interesting to get a sense of how can you find what they are. The generating function is really nice in terms of it's this crank that you can go through. But at some point, you need to know enough algebra to do pattern recognition. This is where machine learning is going to be valuable in your future, that the computer can just check so many different things to try to get a sense of what does it look like. Or the online encyclopedia of integer sequences, and just, does this look like anything? All right, so this is a good place to stop.